Okie dokie. Shall we make a start? Okay, so last week was a fairly full lecture on Friday, and we ended up looking at two situations. We were deriving the amount of radiation generated by an accelerated charge, and we had two pictures. The first picture was one where we calculated the electric field explicitly, and we looked at the far field regime where we assumed that the wavefronts that were being given off, or that radiative zone that's being given off, turns to a plane wave at sufficient distance. We used our previous discussion of the relationship between the electric and magnetic fields in free space to work out that we had a radiating component which goes as 1 over r squared, composed of electric and magnetic fields that each go as 1 over r. Okay? We then, this is an example, I'll just remind you again that you don't need to recall these. These are meant to show you more explicitly, and this is another way of doing the same calculation. We looked at an oscillating current element. This was our dipole picture. And again, we were able to show, by considering the magnetic field generated by that current, when we calculated the vector potential, and then we calculated explicitly, when we did it in spherical polar coordinates, that there was only a phi component for the magnetic field, and that's, as you would expect, the magnetic field goes azimuthally around whatever the current is doing. So the current point is going up, the field points around that way, and the current is going down, the field points the other way. Okay? And by taking the curl of that field, you can obtain the electric field, and you see several components appearing. And we can look at several different regimes. The interesting ones are the near field regime, where we see a dipole-like component appearing, which one might expect. And then the far field regime, when those 1 over r squared and 1 over r cubed components have fallen away, we see, as we would expect, the electric and magnetic fields falling as 1 over r, as we do expect them to do, and therefore when we combine them together, we see the right form for the total power being emitted. And remember, it obeys energy conservation. It falls as 1 over r squared. So we don't need, here we've done it directly from the vector potential. We don't need to do it by making that assumption about the far field radiation. Okay? And as before, as ever, okay, the propagation of the radiation is away from the accelerated charge. It's away, and it's perpendicular to the magnetic field and perpendicular to the electric field. And if you look, and you have to look quite carefully through here. If you look at the ratio of those two fields, they have the correct magnitude, which is that they are about c apart from each other. Remember, this is in free space. Okay. Now, the other thing we pointed out is that the electric and magnetic fields oscillate up and down together. They oscillate in phase. So that's a very important statement. Now, another thing I didn't say is we need to start thinking about the frequency of the radiation that is being emitted. I'm going to say this several times, but notice that the frequency with which the charge oscillates up and down is the same as the frequency with which the electric field oscillates up and down. And that's obviously the frequency of the photons, isn't it? Right? So the frequency of the oscillation is equal to the frequency of the photons. So when I have an oscillating dipole, a Hertzian dipole or any other kind, the frequency of the radiation which is emitted is equal to the frequency of the oscillation. It's a single frequency. Okay? Right. Now let's jump in again. So all that's in the online notes, of course, as ever. Which way around am I? So we had a formula. We said the power, the instantaneous power, as a function of time. We had this I naught squared, and we had L omega squared as well. So there's I naught squared, L squared, omega squared. I do apologise. Zoom that out. There we are. That's better. Okay. We had our, you might call it our power scaling term, 6 pi epsilon naught c cubed, which you see appearing again and again. And you obviously have that time variation of the power, which goes as a sine squared form, because obviously I can't have a negative energy being emitted. Let's look at that equation. what we see, give yourself a bit of space on the notes because we'll give a title to this in a second. What we see is that the emitted power is proportional to the current squared. Right? So we notice that power is proportional to I squared in general. So this suggests something, doesn't it? It suggests that when a charge is accelerated and it emits radiation, the degree to which it emits radiation, that's the radiated power, it's as if the free space around it is providing some form of equivalent resistance. So I can write down an equation, P equals I squared R. Right? But it's not only dependent on some constants. The length over which that current is moving must also be important. Right? So there is an effective resistance. So I'm simply going to naively look at these terms. So this is the proportionality constant, L omega squared over 6 pi epsilon naught c squared. I'm going to define a resistance. And I'm going to define it as L squared omega squared over 6 pi epsilon naught c cubed. So you can see that as the distance over which the current moves grows, the radiation resistance, as we're going to call it, increases and less power is emitted. The same thing is true as the frequency rises. Right? Sorry, as the radiation resistance goes up, the power goes up. Sorry, not down, goes up. So the radiation resistance tells me that as I move the current over a long distance or its frequency rises, the radiation resistance goes up and the amount of power for a given current also goes up. So this is what we call the radiation resistance. And this is an effective resistance that free space exerts somehow. Okay, so it's not like an ordinary resistance or impedance. But let's try and work out what its properties are. Now, let's look at that omega term. We remember, of course, that omega is equal to 2 pi c over lambda. Now, remember what we said there. Remember, omega is the frequency with which the Hertzian dipole itself is oscillating. It is also the frequency of the radiation emitted, so therefore lambda is the wavelength of the emitted radiation. Again, it's a single wavelength. But of course we do remember that c squared is equal to 1 over epsilon naught mu naught. So we can rewrite the radiation resistance in this form. So there's this, see that 3 appearing there? That comes from that 6 we had before. That was that integral, wasn't it, when we integrated power over all angles. That's where that's come from. And we can write it down in 3 equivalent forms, depending on how we're feeling. There is a numerical scaling factor, there is a constant, and then there's a ratio of 2 length scales. There is this effective length over which the charges are moving, L, which we'll clarify a bit more later, and there's the wavelength of the emitted radiation. Clearly this must be an important factor. But I can write it like this, but I can write it in 2 other forms. Notice that epsilon naught c can also be written as 1 over mu naught c, so I can equivalently write this equation as 2 pi over 3 mu naught c L over lambda squared. So it appears that mu naught c, as well as mu naught and c being separately interesting constants, we can write it down as 2 pi over 3. I'm going to give it a new name. I'm going to call it some sort of fundamental resistance. I'm going to call it an impedance, in fact. Okay? But there's still that factor L over lambda squared. Right. How big is this number? Well, let's just calculate. It's dead easy. Of course, it's z naught equals mu naught c equals 1 over epsilon naught c. And if you look carefully, you can convince yourself that is a value given in ohms. And it's 377 ohms. Okay? So that is the impedance of free space, Z0, which you may have encountered in other places. Now, in some textbooks, you will very often see this factor Z0 combined with 2 pi over 3, and you often see it written approximately, but sometimes not very carefully written as being an approximation, that 2 pi Z0 over 3 is approximately 80 pi squared. It's a terrible approximation, but you do sometimes see it written that way. And therefore, the radiation resistance is sometimes written in this form, and you see this a lot in engineering books, because what we're talking about here is antenna theory, and engineers write a lot of books about antenna theory in detail, and they use a lot of numerical approximations, and they write the following approximations. They might write it as 80 pi squared else over lambda squared, and you may also see it written, pi squared is about 10, isn't it, unfortunately. So we sometimes see it written as 800 lambda, or L over lambda squared, or even sometimes that 800 is more properly, it's about 790 really. Okay, so you see these approximations appearing, so do watch out for that. The proper form is 2 pi z0 over 3. Okay. So none of this is perhaps very revealing until we give it some numerical values, right? We're all about the numbers in this course, so let's give an example. And we'll see why this example is important in a minute. We're going to say the length over which the oscillation is taking place is equal to lambda by 4. Okay? In other words, the length of the dipole is 1/4 of a wavelength. That will be important in a little bit. And we're going to assume some fairly large but believable current. The maximum current is like 100 amps. And in this case, the radiation resistance is 50 ohms. And therefore, the power emitted is about 500 kilowatts. Why are these numbers important? Because that is the order of magnitude of the Winter-Hill transmitter. Okay? Puts these numbers into perspective. The Winter-Hill transmitter over there, which I'm going to talk about a few times, is about 1/4 of a wavelength long. Clearly it's emitting over several different frequencies, but order of magnitude is about 1/4 of wavelength, order of magnitude is about 100 amps, order of magnitude about 500 kilowatts. Okay? So don't pin those numbers down too hard in your mind. Okay. All right. So that's our concept of radiation resistance. It's not like a proper resistance. It's really to do with the way that the electrons, as they're moving upwards and downwards, are freeing away, the rate at which they can free away these photons. Now, let's look a little bit more at that. So we talked about oscillating dipoles. And remember, in our discussion of the Hertzian dipole, we looked at the oscillating current element. Let's look at that a little more closely, because there are two ways that we can write down that picture. Okay? So we recall, we're looking at charges, this is our Hertzian dipole picture, charges pushed to and pulled from 2 points separated by some small distance L. Okay? So remember, our picture was as follows. So let's fill in the picture a bit more. We have, and it's important to note this, think of these 2 points, the top and the bottom of our dipole, and one of them has a charge which varies as Q0, some maximum value of the charge at the end, minus I omega t prime. I'm going to put t prime there carefully. Just put that t prime in there carefully for now. And therefore the charge at the other end goes as minus Q0 e to the minus I omega t primed. Okay. And this, of course, in reality is going to be fed by some kind of oscillating supply, clearly oscillating the frequency of emission. And obviously I need to hook them up somehow. And now this is starting to look a little bit like an aerial, isn't it? You can see there's an aerial, and there's a top half and the bottom half. It's very important to notice that they're separated from each other. They're not physically connected. And you will see that in real aerials. We're not quite at the situation of a real aerial yet, but that's where we're headed. So the charge at any particular point, so the charge at the two ends is plus or minus Q0, well, sine omega t primed, if we're writing down the real part of it, and therefore the current, which is our equivalent picture, goes as dq by dt, and again it goes as plus or minus q naught omega cos omega t primed. There's an extra omega that appears there. Okay? In other words, I0, the effective current, is related to the actual charge moving times the frequency with which it moves. Okay? And again, what we're saying is we have two pictures. We have the current picture, which is equivalent to an oscillating dipole moment. Okay? And it's that concept. This is why we call it the concept of the Hertzian dipole is this. Yeah? Hertzian dipole. Okay? Now, when we call it a Hertzian dipole, we haven't actually explicitly said what the dipole moment is. So we can write down a dipole moment. P0 is simply equal to Q0 times whatever the distance over which those charges are moving is. Right? So again, by writing it this way, we can say that the dipole moment as a function of time is equal to P0 sine omega t, which is equal to Q0L sine omega t. Same way. Same meaning. Right. So what? Well, let's look back at that equation there. I was writing down what the total, move this up a little bit. I was writing down what the total power of emission was, and I noticed that there's an I0, there's an L, and there's an omega, which suggests maybe we can write down this I0L, okay, in some other form. Let's try that. We'll try and rewrite I0L. I0L is equal to P0 omega. So therefore that term in the numerator of the power, I0L omega, is equal to P0 omega squared. Okay? Seems like a bit of a cheat, but it's perfectly fine. So now what we do is we say, okay, let's see if we can rewrite that power of emission. So we go back to our equation for the power. There it is again, okay? There's the power of emission, and we're going to average out the sine squared. There's a factor of half going to appear, okay? So we're going to rewrite the total power of emission, we're going to time average it, and we're going to write it in these two forms and see if they're useful. So let's write them out. So the average power for our Hertzian dipole, using our original current picture, is omega squared, L squared, I naught squared, over 12 pi epsilon naught c cubed. So there's a factor of 2 that's appeared from the averaging the sine squared. So I should probably just note that there. Okay? So the factor half comes from averaging that sine squared over time, because it's oscillating. Okay. So this is our current picture. But remember, our current picture was slightly fake because we were tying together I0 and L. What we should really do, which is a better way of writing it, and it will be very important later, is to write it as omega to the fourth P0. So P0 is the amount of charge moving around. That's the magnitude of the dipole moment. And omega is the frequency with which it is moving. So it has the same factor on the bottom, but the importance of this will become much more apparent later. So this is our current picture. This is our dipole picture here. So I'm going to box that in because those two pictures are both important. So these are the Larmor formulas. So I said we have a Larmor formula, right? You can write the Larmor formula in lots of different ways. This is another way to write it. This is the Larmor formula for a Hertzian dipole, and it's obviously here for the time averaged power, because usually it's the total time average power that's most important to see. So with this way of looking at it, you'll see that this omega term here now appears with a power of 4 against it. So imagine I have a certain size of dipole moment, and I vary the frequency with which that dipole moment is changing with time. As I double the frequency, the power goes up by a factor of 16. It's absolutely enormous. Right? And that's a very important number, a very important power to see. That omega to the fourth will appear later. Okay? But the statement is if I have a certain magnitude of dipole, I can imagine a certain amount of charge moving around over a certain distance. If I change the frequency by some factor omega, the power changes by omega to the fourth. It's enormous. Okay. Now, we will come back to that later. But let's just summarize what we were talking about so far, because we're going to move on to real antennas, which should distinguish them from what we've been talking about, which is to define clearly what a Hertzian dipole is. So what do we mean by a Hertzian dipole? A Hertzian dipole. Well, we have implicitly assumed so far, because we haven't said anything different, that the charges are moving non-relativistically. Later, we will see the effect of a relativistic charge motion, which will be, it will change the nature of the radiation quite dramatically. The other thing we said was the source size, okay, L, we were saying was much less than lambda, the emitted wavelength. That's an assumption of the Hertzian dipole. Kind of fudged a bit when we talked about that lambda by 4 above, but we'll ignore that for now. The other thing we say about the Hertzian dipole was that statement we said about the far field radiation. When working out the total amount of power being emitted, we were assuming that we had formed plane wave fronts and that we were in the far field regime. So the observation distance R is much greater than lambda. So there's three scale parameters. There's the wavelength of emission, there was the effective length of the dipole, and there's the distance of observation. And our statement that R is much, much greater than lambda is equivalent to saying that KR is much, much greater than 1. That was that KR that we saw in the time variation of the fields. And the other important thing with all of this is two important statements. Power, P, varies as the current flowing squared, and from that we got the concept of the radiation resistance. And also, power varies enormously strongly to the fourth power of the frequency of oscillation of the charges, of whatever form they are. Okay. Now that's a Hertzian dipole. Any questions so far, by the way? You're allowed to shout out, by the way. Okay, so we should probably fill in that, because real emitting systems are obviously not little idealized segments of oscillating charge. Real systems, as we have suggested, are called antennas. Okay? So they come in a variety of forms, but there are two sort of exemplar or most important examples of what they look like. And the first one to look at is the so-called half-wave antenna. Okay? The half-wave antenna. Now, when we talked about our... remind myself where I am. Yeah, when we talked about our Hertzian dipole, we drew a picture like this, didn't we? We said, here is a segment of distance over which a current is carried. And then we drew another segment down here, and somehow the charges were moving up and down. And they were being fed by some kind of power supply. And I'll just draw that schematic like so. And one thing I can notice straight away from this is to remark that any moving charges, any accelerating charges should be radiating, but as long as I take these two pieces here and place them close together, their radiation fields will cancel, won't they? So this bit here isn't radiating, it's this antenna at the end, that bit, that is. This cancellation is an important idea that we will reflect upon more later on. So this is our real antenna. So these distances, let's put some distance. So we're going to say, let's put a scale on here. So I'm going to draw the amount of current in that real antenna on the horizontal axis, and I'm going to label this. I'm going to call that L over 2. I'm going to call this minus L over 2. That's the length of the antenna. So clearly this is the origin. And I'm going to first make the statement that that distance there, L, is much less than lambda, and that the observation distance far away, over here, R is much, much greater than lambda. Okay? So this is my starting picture for the so-called half-wave antenna. Now don't worry about that scale there just for now. Now, what is the current in the antenna? Well, in this macroscopic object, it clearly cannot be the case that when current is flowing down here, when it tries to flow up, there can't be current falling out the end. The current must fall to zero. So we must already have a picture of there being some form of standing wave, whereby the current, which at any instant is present at the bottom, must be somehow cancelling out with the current that's coming back down again, so that the current at the end is zero. Okay? Current must fall to zero at the ends. So I'm just going to start with a simple picture by drawing it as a triangle. I know it's wrong, right? But I'm just going to say that, just as a very first order of magnitude estimate, I'm going to say that as I feed current in from the ends, it must fall somehow. Sorry, feed current into the middle. It must fall down to zero at the ends, right? So already I have the concept that in a real antenna, the effective current, because of course this observer over here is seeing each of these individual little bits of current, and they're seeing each of those as a Hertzian dipole. I should be adding up all of those little pieces to work out what the total amount of power is over here. Okay? So there's no current at the ends, and with this very simple picture, the effective current must be reduced. And you can see here that if we do it here, if we do it this way, with this simple but wrong picture, it's not completely wrong, the effective current is equal to the peak current that's fed in at the centre of the antenna divided by 2. Right? And to go with that, and therefore the effective length of the antenna, LEFF, we can describe it as being L over 2. Okay? Now when we write it down like that, we can see that the radiation resistance is now different. So a Hertzian dipole has a particular radiation resistance, but a real half-wave antenna in our simple picture must be something like a quarter of that, right? 2 pi Z0 over 3. If I plug in those numbers, you'll see, of course, because this factor here is about 800, that number is about 200 ohms times L over lambda squared. Okay? So again, if we set the length of the antenna to be lambda over 4, right, this is our quarter wave case. That's the example we had before, right? So that's separate from here. This is the half wave. For our previous quarter wave case, where the length of the antenna was about lambda by 4, we have a new radiation resistance, which is the order of 12.5 ohms. Okay, it's lower by a factor of 4 compared to the 50 ohms we had before. Right? What does that mean? That means our Winter Hill transmitter does not give us, for a current of 100 amps, it doesn't give us 500 kilowatts. Our 100 amp, I should put a line there to distinguish them, our 100 amp drive power supply, that's this power supply up here. Sorry, there we go. Zoom that out slightly. So there we go. Okay. Our 100 amp power supply that's driving the antenna, instead of giving me 500 kilowatts, it's now giving me something less. That's the important thing to take away at this point. Okay? So as the radiation resistance drops, the power emitted also drops for a given supply current. About a factor of 4 lower using our simple picture. Okay. Now, let's do that again properly. So let's do the derivation of what is really going on in the half-wave antenna. So I know I'm flipping between half and quarter wave. I was trying to show you that difference in that numerical example. Because it turns out the Winter Hill transmitter is a quarter wave transmitter. So let's do the derivation properly. So again, we're looking at a standard, as you might say, a standard half-wave antenna. Okay. So we'll draw the picture again. Okay. So here is a real antenna. It has two ends, not connected to each other. We have a current that goes out on the top half at the same time as a return current goes in on the bottom half for a given power supply. Okay? And remember that this in reality will be a coaxial transmission line. Right. So if you go into your attic, either yours, somebody else's, and you look for most aerials are on the inside of roofs these days rather than the outside, especially on new built houses, and you'll see there's a coaxial cable that takes the signal from the antenna, and if you look closely at the antenna, it looks like it comes together in the middle, but it doesn't. Right? And again, we're going to set the length of that now to be lambda by 2 in this case, and we remember that in reality we know that the current, if it falls to 0, must be travelling up and down in such a way as to form a standing wave, and we know that that will look like a half sine wave. That's the real pattern of current, and we wish to work out what the total power received at some distance observation point is, and we should really now put in our statement that, remember that for a Hertzian dipole we know that the power observed depends on the angle, should go roughly a sine squared of the angle, shouldn't it? So it should depend on this angle theta, but we remark that for each particular piece of the aerial, which might be at some height r prime, okay, sorry, some height r, we want to figure out how much that current is influencing the total electric field at some distant point compared to r, that observation vector from the origin of the antenna. So we're going to be adding up little pieces of current element, dz, each of which has part of that half sinusoid current profile. Okay? And just to fill in reality, these antennas take the form either of wires or tubes, anything that's conducting really, as long as the transverse dimension is small in comparison to all of these other dimensions. Right? So we were saying that I is in the form of a standing wave. Okay? And we can say it is a standing wave, and we'll see this later when we talk about waveguides. We can say it's a standing wave because we can support a difference in voltage over the length of the antenna transiently because it's high enough frequency. Okay? We can support a change in voltage because it takes time for that knowledge of the voltage to travel from one part of the antenna to the other. So it's true at high frequency. Okay? In other words, our current has a form where I have some overall current, and we're thinking of components IKZ going up and IKZ coming down with a frequency part on top. Okay, so that's the time oscillatory bit on the top. Okay. In other words, the current has some peak value and it varies dependent on the height above the center of the antenna, okay, as so. Okay, so that's the form of the current we are assuming. Okay, it makes physical sense. So I equals 0 at z prime equals plus or minus lambda by 4. That's where that lambda has come from there. Okay, and it's a half wave antenna because lambda equals 2L. Okay. Right, so this is the half wave bit here. That's the thing that makes it a half wave antenna. So what we have to do now to work out the total power emitted is we simply need to work out what the electric field is for each piece of those current elements. Okay? So it's a fairly complex expression. Conceptually it's straightforward. We just need to make sure we follow each of the bits. Okay? So leave yourself some space. So what am I doing? I'm saying I need to calculate from the bottom of the antenna to the top of the antenna. I need to calculate the amount of current that has flown. Okay. Calculate its contribution to the electric field. And then I need two components. I need a sine theta there. So I do apologise. Can someone shut the door up there if it's possible? I tried to do it before. Just so you can swing it shut. It's a bit very noisy out there. Thank you. Okay, so we've got two components. Let's just write them down and then look at them. Okay, so what we're doing is it didn't want to go, did it? No, I can't make it go either. Oh well, thanks for trying. Okay, what are we saying here? We're saying that the electric field, when viewed from a certain distance, is to do with the amount of current flowing. Okay, there's the overall scaling factor. Clearly, the electric field varies at the same frequency that the charges are moving. This is the phase. This is the phase difference between the observation distance with respect to the centre of the antenna and the particular observation distance with respect to that piece of current element. Okay, so there's a phase shift there, right? And then you have this is the sine theta. This sine theta is how the electric field varies as a function of observation angle, average observation angle. Okay, so that's the sine theta that comes from your Larmor radiation pattern. But we need to account for this bit as well, which is the fact that there's a phase shift between the electric fields between the bottom of the antenna and the top of the antenna. Okay, so each dE theta, right? Each dE theta contributes with a different phase. Okay. So they don't all add up in phase, and we can write down that phase as E theta, R of t, okay, goes as 2I over 4 pi epsilon naught c, I naught. When you work it out, you get cos pi over 2 cos theta. So that comes from this integral, okay, taking account of that phase difference there, over sine theta. And then you've got e to the I omega t minus kr, okay. So this bit on the right here, that's just the that's the charges moving up and down, and that's the phase shift with respect. That's basically how far the radiation has gone between where it's generated and where it's seen. And it obviously varies as 1 over r, and that 1 over r has come from over there. Okay? And because it's a far field radiation, okay, whatever's happening with the electric field in theta, there must be a magnetic field going phi, going around. The current goes up, the field goes that way. Yeah? And that looks just the same, except it's got some mu naughts that appear instead of epsilon naughts, okay, to make sure the magnitudes are right, but everything else is the same, right? Cos pi by 2 cos theta over sine theta e to the I omega t minus kr over r. And we recall, as usual, that e theta over b phi is equal to c. So I just wrote those out so you can see explicitly what they are. Okay? Okay. So what we've done is we've simply done this integral, and the notes just go through it in a little bit more detail, but we've simply done this integral to figure out what the effect of having a long aerial actually is. And you get this term appearing here. Okay? Now, our task now is simply to work out how much radiation is emitted by this half-wave antenna. So the Poynting flux is just, let's do the time average. Okay, so there's going to be some factors of 2 appearing. We know it goes as I naught squared. Okay, 8 pi squared, there's 2 factors of pi that appear above, epsilon naught c, and those factors of 2 above have been swallowed up by the 2 factors of 2 that we get from the time average. So we time average these ones, and then we get a cos squared pi by 2 cos theta, okay, over r squared sine squared theta, and obviously the power is pointing in whatever direction, is basically pointing radially outwards, okay? So just to recap what we've done, we've added up, let's push this up a little bit. That integral is saying that we've added up the different phases to do with the fact that the aerial is extended, and therefore there's this phase shift between each of those different parts with respect to the centre of the antenna. This is what this term here is saying, okay? So normally for a Hertzian dipole there'd be a sine squared at the top, but in this particular case the sine squared is at the bottom, and there's an extra cos squared term that's appeared. So this is the consequence of doing that integral over the length of the antenna, okay? Now, we work out the total power just the same as we did before. So this is the power per unit area at a given angle theta. So the total time average power, we do the same thing we did before. We integrate over all angles. So we integrate over 2 pi in the azimuthal direction, remembering that there's no variation of the power in that direction. And we integrate from 0 to pi over theta, where there is a variation. We take the time average of the pointing flux, and we simply multiply it by our area element, r squared sine theta d phi. So that integral over 0 to 2 pi over d phi just becomes 2 pi. Okay? So we write that out. Write it out explicitly, I naught squared over 4 pi epsilon naught c. Okay? There's a factor 2 pi that's gone in there to make the 8 pi squared 4 pi. And I can rewrite the integral over theta like so. Integral from that's right, sorry. This 1 over 2 pi I've extracted from here, so that when I integrate over d phi, okay, this bit here will disappear, and I'm left over with an integral over 0 to pi of cos squared pi by 2 cos theta, okay, cos theta, push that over r squared sine squared theta, okay, but I have this r squared sine squared theta up here, which is my area element. It's a bit of a fortuitous coincidence that those two are the same, d theta d phi. Okay, so this bit here. Let's recap. This bit here is the power as a function of angle and distance, and when I integrate over all angles, I have to multiply by the r squared sine squared theta. Those two terms cancel out. I do apologise for the noise. I can't. Hang on. Shut the door. He really doesn't want to. No, I'm sorry, it won't shut today for some reason. I'll report that. I'll talk louder to finish off. I know it's a bit distracting. The other room's a lot better. It'll be better on Friday. Okay. So what we're doing, we're saying we have I naught squared over 4 pi epsilon naught c, integral between 0 and pi. So the area element of r squared cancels with the 1 over r squared from the distance, so we simply have to integrate this phase term. Okay? And there shouldn't be a 2 there, I'm sorry. One of the sine squares cancel, one of the sines cancels out, but the other one does. So there's a sine theta left at the bottom. There we go. Okay? All right. So what do? We take the power, which goes as 1 over r squared sine squared theta. We integrate over all the angles, remembering there's a 2 pi that appears there. That sine theta cancels with one of the sine squareds there and leaves us with a sine theta at the bottom. And this integral here is only numerically done. And the nice thing about that is it's 1.22. Okay? So what does it mean? It means the average power emitted is about 1.22 I naught squared over 4 pi epsilon naught c. And remember that epsilon naught c, that's the same as the radiation resistance. So therefore, the power emitted by a half-wave antenna is 0.2 times Z0 times whatever the RMS current is. Yeah? So there's another factor 2 that I've put in there. Okay? Remembering that Z0 is 1 over epsilon naught C, and the RMS current is equal to I naught squared over 2. Okay? So that's a different radiation resistance. Right? So just to finish off, we've looked at a Hertzian dipole, and we've found that there is a thing called a radiation resistance that relates the amount of power to the amount of current flowing squared. Okay? But in this case, when we look at the phase difference between the different current elements over a real length antenna, and in this case we've had a half-wave antenna, the radiation resistance in this case turns out to be about 73.1 ohms. Okay? Because 0.194 Z0 is about 73. Okay? So if I have a real half-wave antenna, remember I have to connect it to a power supply. You're probably already aware of impedance matching. Okay? So 73 ohms is fairly close to a standard 75 ohm cable. You're probably aware that cables come in different impedances, and we'll look again at those a bit later when we talk about waveguides. So that the average power emitted by a half-wave antenna, we'll write it one more time, is about 0.194 Z0 I naught squared over 2. Okay, so this is the impedance. It's about 73 I naught squared over 2. And if you connect it to your power supply with a 75 ohm cable, then you won't get any reflections from one end to the other. All right. So how can we use that calculation in a useful way? So we said, if we had, imagine the Winter Hill transmitter, we had something like a 100 amp feed, right? And we had about 500 kilowatts emitted for a quarter wave antenna. But we saw we didn't really get that because the resistance was actually smaller, so we only got maybe 100 kilowatts emitted for 100 amps. We'll turn that calculation round, and just to finish off, let's say we want to get 5 kilowatts of transmitted power out of an antenna. Okay? So as an example. So to obtain 5 kilowatts from our half-wave antenna, we require the current to be 73 I naught squared over 2 to be equal to about 5,000 watts. Okay? Which means that the current has to be about 11.7 amps. Okay? So it shows that 5 kilowatt transmitter is fairly straightforward to get with normal household equipment. Okay? We can make 11 amp supply. So this is like your local pirate radio station, something like this. Okay? You can power it from the mains. Whereas if you want to have Winter Hill, you'll need something a bit more specialist, because you'll need to draw more current to do that. Okay? Now, just to finish off, of course, we've talked about antennas in their transmitting form, and I kind of switch between thinking of transmission and receiving, because of course we're aware that antennas are often used for receiving, like your household TV antenna, if you still use one, or you're not switched to the internet yet. Okay, so the antennas are often used in both ways round, both in transmit and receive. And another interesting example is the example of the car aerial. And one thing you notice about a car aerial is it's usually connected to the roof. Okay? Now the first thing is, of course, it works in reverse. It's receiving rather than transmitting, but obviously you know from the Reciprocity Theorem in physics that receiving and transmitting are much the same. So if I have a theorem, if I have a plane wave passing over the antenna, it will generate the motions of charges, and the same thing happens in reverse, that for a given frequency I can resonate the antenna and it will give me a signal out the other end. Okay? The difference here is that in a car aerial we have a so-called ground plane, and we only have one half of the aerial sitting on the top, and we have some kind of insulation between them, and now the length of that aerial is about lambda by 4. Okay? And we rely on the generation of image currents underneath to give me an effective half-wave antenna. Right? Okay, so this is a mirror signal. So I can use the overall circuits between this antenna and the roof of the car, and the physical length of the antenna is now about lambda by 4, not lambda by 2. Okay? So that's why the Winter Hill transmitter is lambda by 4 in length, because it's using the Earth as a whole as the ground plane. Okay, so it's like the car but bigger. All right. Okay, so we have a ground plane that provides mirror charges. Okay, and in this case, the aerial is now about lambda by 4. So when we talk about half-wave and quarter-wave antennas, really they're the same thing. The difference is whether we have two pieces of the antenna, or one and a ground plane. Okay, I'll leave it there. It's very noisy today. It's lovely and quiet on Friday, and we'll try and get that door fixed for next Monday. We've almost finished section 2. We'll move away, but we want to keep these ideas in mind for when we come back in sections 5 and 6. Okay? The most important thing today is that the frequency of the motion of charge is equal to the frequency of the emission. So keep that one in mind. Okay?